This week on Phys we're hitting legs.
This week, we're working with this problem right here. On this diagram, you can see that this weight is resisting the leg from being extended. We want to figure out how much weight needs to be exerted by FM, or the quadriceps muscle, in order to extend the leg fully.
This is the diagram we made in order to represent the situation. Here we have a vector which is tension. To find the tension, it was mass times gravity, and we came out with a value of 98 newtons. We also use R1 and R2 in order to find FM.
All right, so to solve for FM, we're going to start using the torque equations. We know that net torque is equal to 0 because the diagram is at equilibrium. Next, we know that net torque is equal to the torque of tension plus the torque of FM. And the equation for torque is radius times force times sine theta. So if we come over here and we solve for the torque of tension and FM, we have here that the radius is 0.35, the force is 98, and it is sine 90 because it makes a 90-degree angle right here. Additionally, this is negative because this force will rotate the diagram in a clockwise direction. To solve for FM, we have radius, 0.02 meters. We don't have FM, this is what we're solving for, and sine 90, because this makes, again, a 90-degree angle. And finally, this is positive because the force rotates it in a counterclockwise direction. So now we're going to solve for FM. We take this equation from the last part, and we found that the torque for tension is negative 34.3 newton meters. And then we're going to use the net torque equation and input these. So if we input net torque, we know that it's 0. If we input the torque of tension, we now know that it's negative 34.3. And if we input the torque for FM, we have 0.02 FM sine 90. So here, if we solve, we add 34.3 to the other side, that's positive. We're left with 0.02 FM sine 90. We divide by 0.02 sine 90 to just leave FM on this side. And when we do that, we find that FM is exerting 1,715 newtons of force.
We have exerted 1,715 newtons of force during leg day. That's a good day.